Hello, we are FLL Team 38326, the Electric Mayhem, from Buffalo, New York. For the Into Orbit season, we decided to do research on asteroid mining. Here is what we learned.
On Earth, we need access to many materials and metals to create the technology that we enjoy. We have developed many techniques in order to find what we are looking for. Early miners used a technique called strip mining, where large areas of land were turned over to see what was underground. This was fairly easy, but very destructive to the environment. A more eco-friendly technique for finding deposits is called core sampling. In this technique, a hollow drill bit is used to bring a sample of material up from the ground that represents a cross-section of the material available. From this sample, miners can see if what they want is there and how far down it is.
At this point in history, we have mined most of the easily accessible material, and it is becoming harder and harder to find more. The reality is that there is a limited amount of natural resources on Earth for us to use. Recycling programs can help by reusing materials. Some people have started thinking about fighting the scarcity by just looking for raw materials in new places. Asteroids.
The first asteroid was discovered in 1801 at an observatory in Sicily. It is called Ceres and it is located between Mars and Jupiter. It was then discovered that there are millions of asteroids in this region, and it has been called the Asteroid Belt since the 1850s. Ceres is the biggest asteroid in the belt. It was recently reclassified as a dwarf planet. Asteroids have similar compositions to the terrestrial planets. Asteroids come in three main types: C, S, and M. C-type asteroids contain a lot of carbon. S-type asteroids contain a lot of silicon, and M-type asteroids contain a lot of iron.
Mining an asteroid would be similar to mining Earth. We would have to bring equipment capable of digging into the surface and collecting what we want to keep.
Here is a picture that shows the size of Ceres relative to Earth and the Moon. Ceres is the biggest asteroid in the belt. Most are much smaller. How machines or people would act on an asteroid would change depending on the size. We studied the physics of gravity with one of our high school physics teachers to learn about how gravity works. The strength of gravity on a body like a planet, moon, or asteroid depends on two things: the mass of the object and its radius. The strength of gravity has two main effects. It determines how quickly objects will accelerate towards the ground on these bodies, and it also determines how fast you have to be moving to escape from those bodies. We created a chart to compare values related to gravity for the Earth, Moon, and Ceres. Asteroids can be pretty small. If they are too small, people and machines would fall off of them. We determined that people and machines could exist happily on any asteroid that has a radius bigger than 3.5 kilometers.
Before we can mine an asteroid, we have to determine which ones are worth mining. It would be great to know which asteroids were the ones you wanted before you got there. Each of the three types of asteroids has a different composition and therefore reacts differently when struck by light. This property of materials is called albedo. Surfaces that reflect a large percentage of the light that hits them have a high albedo. Surfaces that absorb a large percentage of the light that hits them have a low albedo. To learn more about albedo, we did some experiments with our LEGO color sensor. We made a set of 6 different toy asteroids and tried to see if we could tell them apart with the sensor. If they were all the same distance away, we could tell them apart, but if the distance varied, we could not. In order to use the color sensors effectively, we would also need a radar system to detect the distance to the samples.
Once you have access to a sample of material, it is easy to figure out what is in it. Mass spectroscopy is a technique that has been around since the 1920s. In this process, a sample of particles is ionized and accelerated through a series of electric and magnetic fields, and then strikes a phosphorus target. The location of strikes on the target can be used to determine the charge and mass of the particles, which clearly identify them. The number of strikes in a given location indicates the relative abundance of the particles in the sample.
The asteroid belt isn't the only place to find asteroids. Some asteroids have been knocked out of the belt due to collisions and gravitational interactions with other planets. Some of these asteroids come really close to the Earth. Sometimes they actually even hit the Earth. Near-Earth objects are not as numerous as asteroids in the belt, but there are over 18,000 of them. Most of these are under 100 meters across. Almost none of them are above 3.5 kilometers across.
Since asteroid mining is potentially very expensive, it would be good to know if the asteroids that you are targeting are worth enough money to justify the process.
We think that it would make sense to build a set of small robotic rockets that will do scouting missions on some of the NEOs near Earth objects. They would be carried close to the NEO targets in a capsule and then be ejected. The landers will be outfitted with active optical scanners like the LEGO color sensors. That means that the sensors will emit light and then will bounce off the asteroid back at a detector window on the sensor. We will use 3 different bands of the spectrum for our sensors: visible, infrared, and radio. This will give us a good fingerprint for the asteroid. After getting the albedo data in each of these bands, the information will be sent back to Earth by radio.
Next, the landers will use a set of servo-mounted thrusters to steer itself toward the asteroid it is interested in. Then it can land on the asteroid to check its composition. Since these are small asteroids, the robots will have small pneumatic harpoons that will attach the robot to the asteroid so they will not fall off. Once the robot is attached, it can scrape samples off the surface. It will use a scoop to gather surface samples and a hollow drill to get a core sample. The robot can scan the samples using mass spectroscopy tests to identify the elements that are there and their relative abundance. After all this data can be sent back to Earth by radio.
On Earth, we can correlate the albedo data with the composition data to get more precise pictures of which asteroids are likely to contain which elements. Once we have that data, it will be much easier to plan larger scale operations in the asteroid belt. We can send larger scale mining robots that will be able to choose which asteroids they should land on based on matching the options in front of them to the data we collected from the NEOs. Thanks for watching our video.